Hi, everyone, and thanks for being here today. We are very excited to have you here with us for this special webinar hosted by VIAS3D. The topic we will explore today is electromagnetic simulation. Explore multi-industry application with VIAS3D. This is a great opportunity to learn how simulation can make a real difference in the way we design and develop products. Faster, smarter, and better. Thank again for taking the time to join us. And now I would like to introduce today's speaker, Yushi Tan. He is the Technical Sales Manager at VIAS3D, where he leads the electromagnetic simulation team. He has over 10 years of experience in the field of microwave and radio frequency, component design, antenna design, electromagnetic compatibility, and electromagnetic interference, signal integrity, and power integrity. Yushi holds a Master of Science in Electrical Engineering from the University of Massachusetts Lowell. He is also a Dassault Systems certified instructor for multiple CST simulation courses. His passion is helping engineers and organizations to optimize their product design process using advanced simulation tools. So with that, let's welcome Yushi, and the floor is yours.
Thank you, Manuel. So welcome everyone to the today's webinar, specializing on electromagnetic simulation. We're going to show you different examples in various industries to showcase the type of application that electromagnetic simulation will be applicable to. So welcome again. Good afternoon, good evening, wherever you are when you're attending the webinar. So I'm going to dive in right now, and I'd like to start with the brief introduction to the audience what VIAS3D basically represents. So how do we execute? How do we function as a company? So at VIAS3D, we have very strong engineering team providing various services. So including the following. So engineering consultancy is one of them, from concept to decommissioning, address your needs to find finished projects where you do not have the expertise, knowledge, or the know-how in-house. So of course you can get the software to design it if you have the bandwidth to do so. And when you don't, we will be able to help as well. So software sales is another area that we are helping with, leveraging the best-in-class solution to address industry challenges and needs. So we are a Dassault Systems value-added reseller, providing various Dassault Systems products, including 3D Experience, CATIA, SolidWorks, Simulia, which Electromagnetics falls under. So also Delmia in manufacturing, and also Innovia in project management. We are especially strong in Simulia, which is the simulation branch, and that's the one of the key focus that we're going to talk about today. So we also provide standard training classes should you ever have the need to get engineers trained up, and custom training is also possible depending on what you need. So design of experiment and optimization services are also available, just FYI, as well as automation and customization. So that's the intro slide out of the way. And we have experts in various aspects and various industries. Let's say take aerospace as an example. There are many types of problems that you can address. And some of the examples are cabin acoustics, composites simulation, structural validation, blast analysis, fluid structures interaction, aerodynamics, well-joined analysis, impact dynamics, vibration friction, failure analysis, antenna array design, EMC, electromagnetic compatibility, and EMI, electromagnetic interference. And RCS simulation is definitely one of the areas that we can help. And not to mention, let's say, antenna placement and cosine interference problems are some of the the typical examples that you would run into when it comes to the aerospace industry. So the topic of today is going to be on electromagnetic simulation only. And if you have needs on any of these different areas, we're happy to connect you with the proper expert to discuss further. All right, so let's talk about the importance of electromagnetic simulation. And let's address what is it to begin with. So I'm assuming you already know the value of doing simulation in the early design stage. So the electromagnetic simulation is a technique to analyze the performance of a component or components. And you have a lot of these components, you form a system using computer models. So you're basically doing the design on a computer instead of building the physical prototype to test it, right? As we all know, building a physical prototype is very costly. And if you have any mistakes in there, when you are in the prototype stage, it will be very costly to make any changes. And not to mention that it's going to delay your time to market, right? So the goal is to predict how specific designs will perform before you even go into the prototyping stage. So basically doing all the early design on the computer as much as possible and as early as possible. That's just general good practice. So there are many benefits to this approach. So we know that making a prototype can be, like I said, expensive, right? So especially when you fail the required tests. So rescheduling these tests can be time consuming and costly in redesigning the prototype, so further delaying your product launch. So simulation allows you to gain additional insight early in the design stage into your model by leveraging the power of visualization. So as an example, you can see how strong the fields are inside the calculation domain very easily. So far-field patterns can also be generated to let you know if a specific coverage is enough for that specific antenna, for example. And then you can also run design of experiments to look at what-if scenarios, right? And all these can be done very easily on the computer. And from there, you can run optimizations to predict the design before moving on to the physical prototyping stage. So like I said, employing simulation early and often helps you prevent late-stage failures and helps you pass your EMC test on the first go. We all know that the products cannot be marketed or sold unless you pass the EMC tests. So various geos have various requirements, and in the States it's FCC, and in other areas they may have other requirements to satisfy. So at least simulation will help you minimize the chance of failing the test, right? So that's the goal. I mean, we want to go into the testing house, first time go. So all these will help reduce costly revisions and help you go to market faster. So that's generally where the simulation values lie. So let's take a look. Here are some of the industries that we serve, and I'm just picking a few examples over here. So we'll be focusing on the high-tech and the aerospace industry here. And of course, simulation covers many industries and many applications. So, I mean, for the sake of time, we're only selecting a few of them to talk about, because I feel like that's somewhat of the more important topics. So in high-tech industry, the boom of semiconductors created a whole new wave of electronic devices. And it's hard to imagine a device without some sort of electronics in it around us nowadays. The most notable being the smartphone that we use almost on a daily basis, right? So it's a pretty powerful computer that we carry around every day, and it can do a lot of great things. So in the transportation and mobility industry, electric vehicles is making a big push for adoption in recent years for their efficiency and also the environmental impact. So with this, the battery development becomes a very important topic for manufacturers. And at the same time, it forces auto suppliers to adapt to this new trend as well. So in the industrial equipment industry, I mean, this is traditionally the slower moving, slower paced industry. And recently we see a lot of, electronics shifting toward the more connected application on this industry. So manufacturing processes gets improved by adopting various tools and workflows. Robots are now running the assembly line instead of humans, right? So all these industrial equipments are getting more and more connected as ever. So as an example, sensors can be placed at various locations of these equipments to sense the soil moisture content to improve the irrigation schedule, as an example. So in the aerospace industry, lots of communication equipment are on the plane to ensure safety first and foremost, and to ensure that the passengers are able to be connected on board. So with the ever-increasing need to stay connected, in-flight connectivity is one of the examples where you may have taken advantage of it already when you're on the plane. You do need antenna arrays on top of the aircraft body to make this happen. So when we talk about communication, antennas is the thing that connects everything together. So wirelessly, obviously. So let me take a look at the typical phone as an example. In the high-tech industry, like I said, this is basically the device that we carry around every day. So the smartphone is a very good example of this. So let's take a look at what goes into the designing of smartphones. So it's somewhat detailed. If you look at the model over here, and of course, it's pretty far from a realistic scenario. We are not measuring, we're not simulating the battery with all the details in it, or the CPU with all the details. So we're not simulating the actual phone for efficiency reasons. So we have in this case, we're looking at the metal frame and the different configurations of the housing itself, and depending on what we are studying, and the multi-layered glass screen. And in addition, it contains numerous parts and also modules. And somewhat realistic PCB design can be seen over here. So you see some of the chips and some of the traces on the PCB and connector, of course. So wireless charging coils can be added in to represent a more premium handset. And with the back being either glass or aluminum, depending on the phone that we're talking about. So premium products typically have a more refined finish, typically using glass to get a premium feel. And cheaper phones more on the budget option typically use plastic to as their back cover. So we were talking about the phone being a communication system here. What are we lacking in this picture? So what's lacking is actually the antenna itself. So in antenna design, there's there are certain challenges that we have to face in modern electronics, and that is the ever-increasing frequency. So let's talk about the sub-6 gigahertz frequency range over here. With design challenges is really in fitting the antenna into, let's say, compact spaces, because the space is also always finite, right? So this is the traditional antenna design area. So think about 3G, 4G, Bluetooth, Wi-Fi that falls kind of into this category. Typical key performance indicators, or KPIs, will be, let's say, total radiated power, specific absorption rate, and also total isotropic sensitivity. And as the frequency spectrum gets more crowded, there's been a shift toward higher frequency bands. So 5G frequency range expanding up to 28 gigahertz comes with a whole new set of challenges, where antenna arrays are used instead of a single antenna to get a more desired performance instead of compared to a standalone antenna. So now the space constraint is not as severe compared to let's say the traditional antenna design, since the higher operating frequency results in a shorter wavelength. So given the same space, we basically have more room, so to speak, right, to work with. Now, integration becomes the key challenge, since we need to make sure that all these different systems need to work properly in a tight space. And the millimeter wave array design fits in this category because of the wavelength being so short. Now, typical KPIs of interest will be equivalent isotropic radiated power, cumulative distribution function, etc. So the difference in the animation over here, it shows you that in the sub-6 gigahertz frequency range, electromagnetic fields penetrate into the phantom model because of the longer wavelength at let's say 6 gigahertz, right? So when it comes to material definition, we really need to model the materials with the proper definition. When we move over to the 28 gigahertz range, now the situation is very different, as you can see it from this animation, right? We can see that the fields generally just stay on the outside of the human body, in this case, the phantom model. So we can kind of take some simplifications to it to make our modeling effort a bit easier. So the two key differences here is that the frequency being different. I mean, a model can be exactly the same. Now, the frequency being different, it brings a whole changes the story basically. Now let's take a look at the existing device with, let's say, 2G, 3G, or 4G, and with the wireless local area network support. Now, all the antennas have matching circuits designed to help achieve the required bandwidth, right? And can we move the antennas from one phone design to another to kind of help, minimize the effort when you have a new product? And the answer is generally no. So you're going to run into a bunch of problems, including space constraints, with the antenna overlapping with, let's say, other parts, right? So that's the obvious obstacle. We can, of course, move it too, but the performance may not be satisfactory anymore. So the antenna may not operate in the frequency of interest, or the return loss is not good enough, right? So not to mention that the matching network will have to be redesigned all over. And since there's so much that you can do, or there's not much you can do, if it is not designed properly to begin with. So what this means is that with a new phone design, you basically have to redesign the antennas as well as the matching network. So it's always the installed performance that matters the most, not just the antenna in isolation. So let's take a look at a couple scenarios over here. So the same exact antenna in 5 different locations. And we can identify the good antenna placement locations. So let's say using the antenna design as is, right? Position 1 and 2 shows, okay performance. And but what happens when you move it to a different location? Let's say 3, 4, 5. Do they still perform the same? Do we still get the similar performance compared to, let's say, location 1 and 2? Like I said, the answer is generally no. When we move it to let's say 3, 4, and 5, we can kind of see that the return loss becomes really bad. All right, so basically reflecting all of our energy back at our source. Right, so we see a little bit of a good performance around 4.5 gigahertz, but that's about it. All right, so the story here is that antenna locations matter a lot. That's because we're basically looking at the installed performance compared to just an antenna in isolation. So when we have situations like this, there's no point of trying to make this work, since the starting point is just not reasonable, right? And you don't want to waste time and effort into this. You might as well just create a whole new design to fit your specific phone body that you are designing. So we have to look at the entire different approach in this, but simulation will give you a whole lot of insight into why this is happening. So that's why the performing simulation early and often in the early design stage is so much, it's providing so much value. So you don't have to deal with any late stage failures or unpredicted obstacles later. So now, like I said, the point is the antenna is not really acting in isolation. The structure actually interacts with the antenna to kind of make the product work as it should. So this is a well-known principle for antenna engineers, but it's nice and useful to be able to visualize it as to what's going on inside, giving you additional information into the model behavior, so you can kind of come up with mitigation techniques, right, if there is a problem with it. So the picture on the left shows that when port 1 is excited, remember antenna port 1 and 2 we saw from the previous slides. So the current flows around the geometry, and we can getting a much better, much higher magnitude. In this case, the surface current magnitude at 2.45 gigahertz. Right. The picture on the right, however, is when port 4 is excited. We can kind of see that in the same scale, we see that the current is not really getting too far from the port area. So basically saying that everything's reflected back at the antenna port. So you're basically not sending energy out of the antenna. So it's not really serving the purpose, right? So modeling the geometry of the phone is clearly very crucial step in in getting reasonable results. So it's actually directly answers the question as to how much we can simplify the model. And sometimes we can make simplifications in certain areas if we know the impact of those details are not so big, right, as to affect our overall performance. And perhaps we can get a faster simulation time. And now areas with high field strength are generally more important when we don't want to simplify the model in those areas too much. because of the high interaction between the fields and the structure. So taking a look at the model a little deeper, now we can kind of look at it from another angle from on the phone design. So glass is typically the material of choice when it comes to high-end phones. Let's say think about the iPhones as an example, right? Since it allows usage of let's say wireless charging. I mean, they're talking about phones without charging ports, right? So you rely on wireless charging to be able to power and recharge your device. So, however, the standard thickness of, let's say, 0.77 millimeter for tough glass suitable for handheld devices is quite far from the optimum thickness of, let's say, 2.05 millimeters in this case. So, we already know that the standard thickness will have a marginal performance. And in order to achieve a good performance while not increasing the outside dimension of the initial design, we can employ certain techniques when it comes to localizing the area to be thickened. So in this case, we're basically building a lens around the antenna array itself, right? So we can definitely propose something like that. And the idea is that we are making a lens concentrating the energy in certain areas, so amplifying it basically to improve the performance of the overall device. So now comparing the glass back with and without the lens, we can kind of see that at bore side, we're not really seeing much of a difference in terms of, let's say, pattern. They look very similar, right? We may be asking ourselves, hey, why go through the effort and trouble to thicken the glass to make it a lens, since it's going to increase the engineering effort and also the manufacturing cost. So notice that this is just at bore side, right? So much more is going on when you look at the model from another angle. So now, before we go further, let's take a look at the S parameter, right? So with and without the lens, and I think the difference is pretty obvious. Now, the impact of the lens is definitely there. Now, it's going to help with minimizing the return loss, basically, right? So the reflected energy back to our source is a lot lower with the lens compared to without the lens. So, I mean, you can clearly see the difference here. I mean, that's why we do this to begin with. So with the lens, it's going to improve the performance. Now, this in turn affects basically the efficiency of the module directly with the lens. So we're getting less than 50% efficiency at best without the lens, but with the lens, it's going to improve to over 70%, right? So in terms of let's say total efficiency, that's a very important metric to look at when you talk about how much radiated energy is getting out of the antenna itself. So like I said, the radiated energy needs to be going out to the device. Now at theta equals 30 degrees, we can clearly see that the model with the lens is going to give us a little bit of a better coverage at this specific angle. Right now, the antenna array is not going to perform at bore side only. It's going to have to scan around to make sure you get the reception that you need. So I think, Manuel, at this point, let's pause a bit and start the first poll question.
All right, sure. So you guys able to see the poll question? So we have 2 votes so far.
Okay, let's give it a minute, or maybe 20 more seconds.
Yeah.
To get the results. Okay, so Manuel, are we Are we okay with the polls?
Yes.
Okay. So how many percent of the attendees actually use simulation currently?
66%.
Okay, so that's good. That's good. I mean, there's a good mix, right? I mean, that's why we host these webinars to bring awareness to companies and individuals who are in this space when it comes to designing. Like I said, simulation's most valuable aspect is actually in the early prevention stage. Okay, that's good. Thank you all for the for answering the poll questions. All right, so let me come back to the presentation, and I'm going to switch gear just a little bit to talk about, let's say, from to get away from phone antenna designs, right? I mean, of course, everything's related, so we're still in the high tech area. Now, let's talk about the electromagnetic compatibility, or EMC, and also signal integrity and power integrity, SIPI. So if we look at a typical prototype and see how certifications are done, we need to know that, well, we all know that the physics are included because you're basically testing the device in practice, right? So what it gives you is that whether the device passes or fails. So no further information in general, right? Performing simulation, it offers much more before you even get to that stage. So you do not need a physical prototype to simulate, but of course you need to catch geometry and the material definition to be able to model it correctly, right? To work on the computer to get some performance out of it. Now you can easily set this up by using parameters, so you can change the model and you can potentially optimize it later on before you even move to the physical prototype. So you can see that the difference between variations to gain better understanding on how the mitigation techniques can be employed if you run into problems later down the road. Now, all that is possible through powerful 3D visualization, for example, surface currents, electric and magnetic fields inside a model. And if you have an open boundary problems, far field visualizations can be seen in previous slides in terms of, let's say, an antenna pattern. All right, so all this sets you up for success, so you don't have to build a prototype, costly prototype, and that may potentially fail. So we're not saying that simulation is going to replace measurement right now, right? But you should look at it as, look at simulation as a complementary tool to measurement. So in other words, you should use simulation as a pre-compliance tool to ensure, success when you do get to that measurement stage. So oftentimes we are asked this question, hey, how do we know that the simulation result is trustworthy, right? You can definitely have to model what you're measuring. In terms of EMC, as an example, there are publicly available information on this. Imagine you have a model like the one shown in the picture, right? And this is taken from a paper published by on IEEE. So where the detailed model is simulated, and there are some vent holes in the box to allow for fields to escape to or pass through when internal source is excited. Now we can build an equivalent model representing these square vent holes with compact vent models to help with meshing. Now we are presenting this, so you already know that the result's going to look pretty good. But like I said, this is a published result, so measurement was actually performed. And I'm going to show you what that measurement looks like in the next slide. So multiple cases are compared over here. Now the red curve is really from the measured result at Missouri Science and Technology University. Now the blue curve is from, let's say, modeling with 16 cells per wavelength in the detailed model. And as we increase the cells per wavelength to a, let's say, higher number, right? Let's say 100 cells per wavelength. Now the mesh is really fine. Now the result generally increase in accuracy, but not by a whole lot, as shown in this picture. So this shows the behavior of the model, which is a common technique to make sure that the results converge, right? You're increasing the mesh, finer and finer resolution, but your model result does not really change by much. So that's when we know the model is converged. So if you look at, take a look at the green curve. Now that's represented by the TLM compact model. So we have various modeling techniques to make our simulation run a little quicker, but at the same time not sacrificing accuracy. So we're still capturing the same behavior, or I should say some very similar behavior, right? But at much higher speed, basically. So you can see that the results compare really well with measurement. So ultimately, that's what's important. But you do, like I said, I need to emphasize this enough. You need to model what you're you need to simulate what you're measuring, right? Apple to apple comparison. So, and of course, we're measuring the fields at a certain distance away. In this case, let's say far field at 3 meters. And if you're interested in the near field region, the geometric detail may have significant contribution in the area then that you're interested in. And you should definitely discretize these areas with good enough resolution to make sure that the effects are accounted for to get the accurate solution. And like I said, the reference actually on the bottom for interested audience. You can go there and read that paper. Now, let's talk about the electromagnetic simulation in signal integrity and power integrity area. So transmission lines take many different forms, but they all serve certain purposes and have one thing in common: to carry electromagnetic energy from one place to another. So typically, different systems are connected with these transmission lines. One form of the transmission line is actually the wire harness itself. So you can start the routing on a schematic, but the actual routing will have to be done on in 3D because it's really capturing all the effects. So depends on what you view as interesting. I mean, there's definitely more going on in 3D compared to the schematic. As an example, unshielded twisted pairs can easily introduce common mode currents, or when the pair is not perfectly matched. It can happen in the excitation and also in the middle of the twisted pair itself due to, let's say, kinks and bends, etc. So it's going to be reflected in the S parameter when you perform the simulation. So this common mode current can then introduce radiation from the cabling system to potentially affect other parts of the system. So now the interconnects and also the connectors can be modeled and simulated in full 3D to capture all the effects. Like I said, twisted pairs, splaying, similar to kinks and bends, all have some kind of effect on the signal integrity. So higher bandwidth, higher frequency applications require pretty tight tolerances on signal integrity. And automotive CAN buses, we have the specific set of rules to follow. So the point is to use full 3D simulation. You'll be able to simulate various systems that's connected by cabling. You can also simulate a short section of the cable to see the effect as well. Right, so full 3D is generally not feasible for these type of situations because of the complex geometry captured, and also the length of the cable may be a lot longer compared to, let's say, the details of the model. So the aspect ratio is quite big, so that makes the simulation very inefficient when you have that kind of scenario. And multiple techniques can be employed to make this more manageable. And you can leverage these techniques to capture the signal integrity part and also bring that into full 3D. Now on the right, we see such a case, right? We have the cross section of the cable, where you can represent the full length of the cable using some kind of equivalent modeling technique. Now you can, of course, get the S parameters from it. And what's more interesting is that, when you represent this cable in full 3D, any common mode coming from this cable can be represented. So as visualized in this plot over here, you can see clearly that the field from the box on the right is interacting with the cabling in the middle, right, connecting the two boxes. Now the cable in the middle can interact with the fields in full 3D to basically give you the bidirectional coupling between the cabling and also the 3D environment, which in turn connects to the source of these antennas as well. Right, so I'm going to switch gear a little bit. Now, the Internet of Things market is really expected to grow significantly in the coming years with the advent of 5G technologies and beyond. Now, we see a lot of these smartwatches nowadays, and hearing aids has been around for a very long time, and pacemakers for patients who need it. And we're kind of venturing into the life science industry. So that's a second topic that I want to talk about, or I should say industry that I want to talk about, on top of the high-tech industry. Now, all these applications are very important. Now, thermal treatment is, let's say, cancer treatment. They employ some kind of electrode inserted into a certain area, localizing the heating of tissue. in these areas to make sure that the cancer cells are treated or burned properly without damaging the healthy cells. Now, we can also simulate hypothermia. And in terms of imaging, MRI machines are pretty typical. You can have a pretty detailed model in the human model, biological model, to run the MRI simulation. Of course, when it comes to microwave imaging, is another area that we can leverage simulation to get a good insight into what the outcome is going to be. All right. So in terms of, let's say, biomodels, the level of details of these models depend on the application itself. So, for example, for SAR calculations, maybe all you need is just a homogeneous phantom model to mimic the certification test. Right. And since the material definition is homogeneous, you can get the results in pretty quick, right? To get a ballpark figure. Now, if you need the full detail, you can get a more sophisticated model in your simulation. For example, voxel model. So typically, these models can be quite detailed. Most of the models you're able to get down to what's, let's say, 1 millimeter resolution. And most of them offer multiple resolutions depending on what you need in terms of, let's say, the certification. So there's a wide variety of voxel models available, including baby, child, adult, male, female, even animal models are available if there's such a need to perform these calculations. And now multiple cat models are also available, both in male and female, so you can account for all these different scenarios. So these cat models include details like blood, cartilage, fat, skin, bone, organs like kidneys, bladders, colon, you name it, right? So a lot of these details all depends on how much need you have when it comes to performing these simulations. So that means you can use the frequency domain tetrahedral mesh to simulate it for a lot of these cat models on the right. And these models are based on the US National Library of Medicines for a Visible Human project. So which a frozen corpse was dissected and photographed, the full model can be simulated. And of course, that part of the model can be simulated as well to localize the area that you are trying to represent. Now, to be able to parameterize the model to, let's say, to mimic the breathing sequence, that is also possible. So that's the animation we are seeing here. And the plane wave is an incident on the model. And right now, we're basically seeing that the animation of the plane wave being incident on the model. So basically giving you a whole lot of insight into what's actually happening when you breathe and the various areas that are showing, let's say, high field strength. That kind of gives you more and more information before you go into testing. And typically you don't test on humans anyway. So a lot of these cases can really show the value in simulation. So we have a very important topic to talk about when it comes to human safety, since we cannot really easily or comfortably measure inside the body. So on the left here, we see a homogeneous phantom where a cylindrical or block of shape is made out of plastic and then filled with some kind of fluid to imitate the body tissue properties for easy simulation. And in the middle, we have the homogeneous head model. So it's a little more detailed compared to, let's say, the cylinder model. Now on the right, we have all the features included in the simulation. We can kind of see that the local heating is very different when it comes to this, right? So the detail model will definitely be a little more challenging, but you capture way more detail in terms of, let's say, what tissue is being heated up, etc. And that's going to give you the more realistic scenario. So looking at the, let's say, temperature, for example. Now on the left, we see the homogenized head model, no bioheat being included. Now on the right, we see a heterogeneous model with a lot of details being included with bioheat. Now we can kind of see that the results clearly different, right? And also the hotspots are very different as well. So on the right, we're definitely getting a much higher fidelity in terms of results. So Yeah, like I said, the resolution can go down to 1 millimeter, sometimes even half a millimeter if you need it, depending on the model you use. So these are quite detailed in terms of giving you a good results. All right, so let's pause again to take the second poll question, Manuel.
Right. So the poll is already active.
All right, let's give it a minute and we'll talk about the results briefly and we will move on to the next topic.
Okay.
Okay, Manuel, are we getting all the participations from our audience?
So we have 80% of responses now, and 75% voted yes on the question if they are interested in multiphysics simulation capabilities.
Yep. So that's a good chunk of the audience is actually interested in multiphysics. I mean, it's a very important aspect of the simulation because what you are testing is, in practice, is actually a multiphysics problem that you're trying to solve. Okay, that's good to hear. All right, so let me move on to the last topic of the day. It's really in aerospace. I'm going to focus on the antenna portion of it. We kind of talked about it in a little bit in the high-tech slides, but over here, we're basically talking about an airplane in the aerospace industry. So the airplane can have a lot of these antennas built in for communication and for safety, etc., and for connectivity. Right, so we have VHF antennas and in various locations. I mean, just a fictitious mock-up of the plane itself. So it's not really representing the actual scenario. The actual scenario may have a lot more antennas than what we're showing here. But we're here to illustrate the point, basically. So we have GPS antennas for safety, so you can kind of know where the plane is at any given time, and also know the location of it, right? So the various altitude measuring antennas can be included as well, and of course, communication is one key aspect of this. And we have all these different antennas on the aircraft. Are they interfering with one another? I mean, that's typically the question that one would ask. And also, when you install the antenna on an airplane, does it really change the behavior of it compared to isolation? And like I said, all these installed performance is actually what matters the most, right? So not an antenna in isolation. So here's an animation of the, let's say the field radiating from the VHF antennas on the plane at various locations. So you kind of see that the interaction is very different. Now the first one near the cockpit, it's going to penetrate into it, the plane a little bit, and whereas mounted on the bottom, we don't really see much of an interaction inside the cabin of the plane. So it's quite interesting to see that just due to the location difference itself. Now, and of course, like I said, the antenna installed performance, let's say on the left, we have some kind of ideal antenna on a perfectly flat ground plane, right? Mimicking the actual antenna in isolation. Now, when we install this antenna on the platform, let's say in this case, an airplane, the shape of the airplane will actually change how the far field will look, right? So that is also it's always the most important aspect. The installed performance is what one should be looking at when designing these systems. And looking at it from another angle, so this is the surface current plot when it comes to the VHF mounted in the rear of the aircraft. Now the whole aircraft is actually becoming an antenna. You can kind of see that it's radiating, or surface current is flowing on the skin of the aircraft, right, making it somewhat of an antenna, mimicking device. So the level of impact on the pattern depends on various factors. So the first one is antenna type. Now the second one is actually antenna position. And the third is, of course, the wavelength, right? What frequency the antenna is operating in. Now, the VHF blade uses the aircraft as the ground plane, so the aircraft geometry has really strong influence in the performance of the VHF antenna itself. Now, another aspect to consider is actually in the location of the antenna mounting point, because when aircraft fly in the air, they may be struck by lightning. And I think statistically speaking, we are seeing a lot of these lightning strikes happening, but due to the properly designed aircraft, and a lot of times we just don't see the effect of it. And we design these aircrafts pretty well to kind of minimize the chances of getting struck by lightning as well, in the form of, let's say, positioning of the antenna, the shape we use on the airplane, etc. So taking a look at this a little further, now we may have different systems. The last topic is going to address the co-site interference part of it. Now you can have multiple antennas, so the DME, the VHF, GPS, for example. Now you can kind of take a look at the coupling between them, but I mean the main thing we're trying to address is make sure that the antennas don't really interfere with one another, because they need to operate at the same time. So it's not going to say that, hey, you have one system active and then all systems needs to be, inactive for that to be functioning, right? That's not realistic, right? So all systems need to be performing at the same time, basically. So here is the plot of the various antennas. So the VHF, DME, and GPS, and we can see that the corresponding coupling between the two. So let's say when GPS antenna is active, and the VHF antenna is active, and how much is coupling is getting to, let's say, the GPS antenna and also the DME antenna, right? So that's just one area to look at, and also we can kind of take a look at the spacing between these antennas. So in this case, right, let's say the VHF antenna to the GPS antenna separation is 2 meters or so. Now, when the VHF antenna is transmitting, now it's clearly showing some kind of interference to the GPS antenna, right, in receiving mode. Now, this is actually not, acceptable, right? So what if we change the separation between the two? It's going to be improving to a point where this is reasonable or acceptable. The answer is still no. I mean, performing simulation gives you these ideas, so you don't really spend time in relocating the antenna, because cabling needs to be involved, right? So you do a lot of these analysis on the computer before you even get to a production stage. So what can we do? We can employ some kind of filter to filter out the frequency contents that we don't need, right? And that is to make sure that the frequency range is proper before we mount the antenna on there. So we can kind of see that the result of the VHF antenna output, how much is getting to the GPS and also the DME when the VHF are being transmitted. So in this case, VHF, GPS coupling can be seen over here. Now we can see that the black curve is actually the before picture, and the green curve is actually what's after by employing the filter. So let's take a look at the results real quick. Now, VHF antenna by employing the filter. So filter, like I said, filter is basically acting as some kind of passband, right? So filter out the frequency contents that you don't need. So the coupling is not going to get to the GPS antenna. So that's what we see here. So VHF as in transmit mode, and the interference to the GPS antenna in receiving mode is no longer an issue. All right, so that's the basically the key point we're trying to highlight over here. So I think that's all I have, and I guess at this point, if you have any questions, let's address these.
All right. Thank you so much, Yushi. Thank you, everyone, for attending. So seems like we don't have any question here. Well, we obviously encourage you, if you have any further question, if you want to learn more, please drop your question here and we can address them. So let's give it a couple of minutes now and see if we have any question.
Yep. Okay.
All right. So it seems like we have a first question right here, which is for electrically large models. Is there any efficient way to make the simulation speed manageable?
Yes. So there's always methods that you can employ to make the simulation more manageable. The compact model that I showed a little earlier is one such approach, but for complex, let's say antenna type of model, you can most certainly just extract the fields around the antenna and then later on use this extracted field in a much bigger environment to use the extracted field as an excitation, kind of kind of get around the meshing requirement using one brute force method. So yeah, there are various techniques that you can employ. So the technique that I just talked about is called the hybrid solver approach, basically leveraging the best of each solver to be able to get the solution on the system level.
Right. Thank you so much, Yushi. We have another question right here, which is how many solvers are there in the CST Studio suite?
Yeah, so there should be around 30, depending on what you mean by solver. So I think I would say, the way I look at it, 30 or so application-specific solvers in CST to address various applications.
All right, perfect. And seems like we have one last question, which is, do you guys offer engineering services in case we need you to perform some electromagnetic simulation?
Yes. So service is definitely one thing that we do compared to our, let's say, I wouldn't say competitors, but other value-added resellers. So if you have interest in certain areas, we are more than happy to connect you with the proper expert to further the discussion.
Right. Perfect.
Yeah. So the info can be found over here in on the slide over here. So info@VIAS3D.com is one way to get in touch with us, and you can also give us a call at 832-301-0881 as well.
Thank you so much, Yushi. We have one more question here. It says, thank you, Yushi, for the presentation. Will there be any session on the simulation techniques for metamaterials, fully passive electromagnetic structures?
Currently, we don't have anything planned, but if there's interest, we can definitely make it happen.
So, seems like there are no more further questions. Again, thank you, Yushi, for that great presentation. Thank you, everyone, for attending. And that brings us to the end of our session today. We really appreciate the time, and we really hope that you found this session helpful. If you have more questions or if you want to learn more, feel free to connect with us after the webinar. And take care. See you next time.
Thank you, everyone.